In this video, I'm going to give you some examples of calculations of rates of change of functions. Okay, so suppose I had a function f of t equals 6t plus 4, and I wanted to know the rate of change of that function. Now, what do I mean by rate of change? So that means that's a certain ratio. So let's get that clear. Rate of change of f of t is the change in the function relative to how much I have to change the time in order to get that change. All right, and so this should be clear that this is a linear function, and so that's going to give the slope, which is 6. Okay, if that wasn't clear, you can pick any 2 points, like f of 2 minus f of 1 and 2 minus 1 for the time values, final and initial. And so you would see, let's see, f of 2 would be 16, f of 1 would be 10, f of 2, 12, and 4, yeah, 16, 2 minus 1, so yeah, that gives 6. All right, so that's the rate of change, and later on we'll do more complicated rates of change. Now, let me discuss well, let's do a little bit more complicated one now. Let's do one where the rate of change is not the same everywhere. All right, let's talk about piecewise defined functions. Okay, so let's say I had f of t, and it was it equaled a certain expression for certain times, and then a different expression for different times. So like maybe 2t plus 3 for t in between 0 and 5, and then maybe minus 3t plus let's see, 28 for t greater than 5. Okay, so you can calculate the rate of change for each part of the interval. Okay, if you were to graph this, you would have you'd have a line segment for each portion. Okay, I'll go ahead and sketch that right now. So at 0 it goes through 3, and then at 5 it goes through 13. So something up there. So the line for the first part would be this, okay? And then for the second part at 5, I have 13, and then let's pick a different one. Let's try 10. At 10, I have minus 2, so that would be down here, and so the graph would be like this. Now, you could imagine having multiple pieces. Okay, here I have a piece from 0 to 5 and then after 5, but I could have added like a piece for from 5 to 10, and then from 10 to 15, etc., etc. So you could imagine the graph being a zigzag, having all kinds of line segments joined together. Okay, so piecewise defined functions. And then for this one, we would say that for the how about if you try to calculate the rate of change for each of the 2 pieces of this function. I'll try that now, and then I'll tell you what the answer is in a minute. All right, so for the first piece, the answer is still the slope. So this would right here, it would be 2, and then for the other one it would be the slope, so that would be minus 3. Okay, piecewise defined functions. Now, you could also have there's a specific type of piecewise defined function. Imagine that you had the following simple function, or simpler than the last example. What if it was 5 for t between 0 and 10, and then let's say it was minus 3 for t between 10 and or for bigger than 10 all the way to 20, and then maybe it was 0 for 20 to 30. So that's perfectly fine. There's no reason it can't be a constant. And we know that a constant makes a horizontal line segment. So let me graph this one. Okay, and so the for the first 10 seconds it's 5, then it jumps down to minus 3 for the next 10 seconds, and then it goes to 0 for the next 10 seconds. So the graph would look something like this. Okay, when you have a piecewise defined function that is filled with pieces that are constant, well, you can refer to this as a piecewise constant function for obvious reasons. Okay? So what would be the rate of change for each of the pieces of this function? Take a minute to think about that now, and then I'll write the answer. Okay, so for all 3 intervals, there's no change. So 0, 0, 0. Okay, now that's not to say that the function never changes values. Okay, if within the interior of each of those intervals, it's certainly not changing. All right, but what about if I asked you a different question, like how much does it change for the first 20 degrees, for the first 20, oh, actually my horizontal axis should be time. So for the first 20 seconds, okay, well then we would calculate the change in y, or the change in f versus time, and at t equal 20, so f of 20 minus f of 0, and then the delta t. At 20 it's 0, at f of 20 is 0, f of 0 is 5. Okay, so this would give minus a fourth. That's perfectly fine. Okay, that's kind of giving a rough idea of the change. It's not really a line, so you might be a little uncomfortable using the slope equation for something that's not a line. We certainly don't have a line between 0 and 20. We have actually line segments going in all kinds of different directions. So think of this as kind of a rough, think of it as like the best we can do, since we don't have a single line between 0 and 20. All right, and then we could do something similar for 0 to 30. Okay, and that would give us, actually the top would be about the same. It would be exactly the same, f of 30 minus f of 0, and then 30 minus 0. So 0 minus 5 over 30, that would give minus a sixth. Okay? Just a heads up, the reason that I am emphasizing piecewise constant and piecewise defined functions is we're going to get to some more complicated situations that we're going to approximate them by piecewise constant and piecewise defined functions. Okay, so make sure you understand how to find the rates of change for these specific examples.